Okay, this is Dr. Morton. What I'm going to do is I'm going to talk about problem 6, and I'll just post this as a short separate video because there was a student that asked about problem 2 for homework set 6, so I'll talk about that a little bit, and then I'll do a lecture on the review. All right, so so let's look at this. So here's homework 6, and so if we flip it to this page, then you can see we're going to look at this second problem, and I think this is identical to the lab we did. You can see here's the lab, and you can see that these are identical. So what you can actually do, since you have this already programmed, you can just put it on your board and execute it and see what state it actually goes to. So that's one good way of checking. But let's just go through this briefly. So so if I draw this out like this, let me turn on the light so you can see it. There we go. Okay, so yeah, it's not too bad. So here's my clock up here, and we start in state S0, and our first inputs. So remember, one of the things you have to understand is that these vertical lines are the active clock edge, the rising edge of the clock, and then it's up for a little bit, and then it goes down, and then it has another rising edge. At each rising edge, we change states, but the inputs change between the edges, and I'm just going to, for simplicity, I'm going to assume that the inputs are going to be good by the time the clock falls again. So the rising edge, the flip-flops change, then we have a potential for false outputs here. We don't want to read the outputs here because the new inputs haven't arrived, and the mealy inputs will be driven by the new clock, by the new inputs. So the new inputs will come in here, and I'm not going to draw any false outputs, but of course there would be false outputs because until the new inputs come, we would be operating on the old inputs. And then when the new inputs come, say in this case, the old inputs are 1, the new inputs are 0. That's X2. So that would actually, well, in state S2 and S3, there are no mealy outputs. But in state S1, in state S0, there are mealy outputs. Potentially 3 of them, Z1, Z2, and Z3. So in state S0, we could have false outputs until the new inputs are good. But I'm going to ignore that. And I'm fine with that. You don't have to worry about that. But if you want to put those in, that's fine. All right. So what I do then is, at each clock edge, I have my new inputs and my current state. So my current state is S0. My new inputs are 1, or X1 is 0, X2 is 1, X3 is 1. So 0, 1, 1. And that's how I think I wrote them. Yeah. And so if we look at the chart, we realize that, let's see, let me transition that. We realize that we're in S0 here. I'll get rid of this, and I'll blow this one up a little bit. Actually, I can't. Okay, I think it's big enough. So we're in state S0, and our inputs are 0, 1, 1, and so that means X2 is a 1, so we're down here. We have a Z1 output, so Z1 equals 1, and then we check X1, and X1 in this case is a 0, so that means we go down this path. We output Z3, and then we come over here, and we're going to go to on the next rising clock edge. Rising clock edge. We're going to go to state S2. So I write S2 in, and then we'll assume the inputs are good halfway through. So X3 then, so X1, 2, 3 for the second set would be 1, 0, 1. All right, so that's 1, 0, 1. And then we look here, so we're in S3, and the only thing we're really going to check is X1. x1 is a 1, so we're going to go back to S0. And then our outputs, the only output is a more output, and it is associated with the state S2. And so, sorry, it's Z1. It's state S2, but the output Z1. So our output Z1 stays up, and the other outputs go low. Let's see. Let me transition that. So our Z1 stays up, Z3 goes down, and Z2 stays down. And now our next clock edge comes, and our new inputs are 1, 0, 1. So since we're in state S2, x1 is a 0. X1 is a 1. So that's going to send us back to S0. And then S0, our new inputs are 1, 1, 1. And so 1, 1, 1. That's gonna send us back to S2 again. So now we're in S2, and our new inputs are 0, 1, 0. So the only one we check is X1. It's a 0. So now we're going to go to S1, and we're going to output Z1, of course, because we're in S2. When we go to S1, we're going to continue to output Z1, regardless of the new inputs, because it's a more output. For Z1 has both mealy and more components, but this one is the more. And then our new inputs are 0, 1, 1. And so we just continue to follow this analysis like we've been doing. So that's how we would solve this. And yeah, it's pretty straightforward. So let me transition back in here, actually, to, yeah. Okay, so that's how we would do this. That's how we would solve the problem. And also, so that's part A. Use the state assignment AB 0, 0, 0, 1, and 1, 0. That's the same assignment we also used on the lab. And so, so I did solve these in class, or most of them. So the ones that are straightforward. So we'll take a look at those. So let's see. I'll do this. Okay. So if you look at this, yeah. So let's do the flip-flop input. So we have two flip-flops, and A and B, or whatever you want to call them, and we call them Q1 and Q0, but we'll call them A and B here. And so 0, 0, 0, 1, and 1, 0 for these three states, and then there's a don't care state of 1, 1. So we have to account for all the paths in where A is a 1. Well, it's just S2. How many paths into S2 do we have? Well, so we've got a path that comes from S1. So that's going to be so let me transition over here. Let's see. Yeah. Okay, so that's going to be so it comes from S1, which was A prime B, and then it's requires X2 to be a 1, so X2. And then we want to add to that the other path. Now this path comes from, you can see, we're in S0, and we come, X2 is a 1, X1 is a 0, that's one path, and then we also have the path X2 is a 1, X1 is a 1, X3 is a 1. So we have actually two different paths that come into S2 from S0. So we have to write both those paths. So it's going to be A prime, B prime, x2 x1 prime, and a prime b prime x2 x1 x3. All right, so let's write that. So it's going to be a prime b prime x2, which has to be a 1 in both cases, and then in one case x1 is x1 prime, and then the other case it's a prime b prime x2 x1 and x3. And then we can simplify that a little bit maybe. So we have a prime b prime x2, and maybe we can't. Yeah, so we actually have, we can write this a prime b prime x2 times x1 prime plus x1 x3, and then we know in this case we should be able to eliminate the x1 here. So x1 prime x3. Yeah. Sorry, we can just write it like that, but we should be able to get rid of this term because of the x1 prime here. And so this equals our d sub a, and our d sub b then is just going to be all the paths into S1. And there are 3 paths, well, yeah, there's 3 paths into S1. 2 of them come from S0. So there's an A prime, B prime, and then X2 prime. That's one path. And then there's an A prime, B prime, X2, and X1 and X3 prime. And then, so that's 2 paths in from S0, and then you do have a path from S2, and that one's going to be plus A B prime, and then we have A B prime and X1 prime. X1 prime. So that's pretty much it for the 2 flip-flop inputs. And then the only output that's tricky is S2. Sorry, Z1. Z1, because Z1 has the 2 mores, so Z1 equals A prime B plus A B prime plus then the when it also shows up in S0, which is A prime B prime X2. And yeah, so those are the 3 times when we have X1 showing up. I'm sorry, Z1 showing up. And then the other one, Z2, is pretty straightforward. So if we look at this, we can see that Z2 only shows up here. So that's A prime B prime X2 prime. So A prime B prime X2 prime plus, that's the only time when Z2 shows up. So that's it. And then and we did Z1 already, and then Z3. Z3 only shows up when we're in A prime B prime X2 X1 prime. So Z3, let's transition again. Z3 equals A prime B prime X2 X1 prime. No, just x1. No prime. Yeah. And that's the only time we see z3. Okay. All right, so I think that's all of them, so you can check your work with that. But that's how we solve those. And then if we look at the other components, so we have realize the chart using PLA and D flip flops. Give the PLA table. I'm not gonna. I don't think I defined what PLA I wanted you to use, so I'm not going to worry about that. But if we used a ROM instead of a PLA, so basically, once you have the equations, you can if once I give you the PLA, you can have that. But I don't care that you do that one. But if a ROM is used instead of a PLA, what size ROM is required? And since we did this in the lab, you should know that. So that we have to have. We address it, so the ROM is going to be addressed with the 3 inputs and the state, which is A and B. So there are 5 bits for the input address, and then the outputs are Z1, Z2, Z3, and then DA and the D sub A input and the D sub B input. So there are 5 columns, and so we're going to have, if we have 5 address lines, that's 32 rows, and we have 5 columns. So it's a 32 by 5 ROM, and that's what it's going to take. And I think that's it. Yeah. Okay. And yeah, I think that's it. All right. So I think I'll just go ahead and stop with that, and that should give you a boost up on getting that problem done.